Okay, so number 4. What orbital speed must a satellite whose mass is 800 kilograms have in order to maintain an orbit 2 times 10 to the 7th meters above the surface of Jupiter, where the gravitational field strength, in other words, little g or AC, because they're the same thing, is 15 meters per second squared? Okay, and what would it weigh at this height? So we're looking for orbital speed and then FG. So first we need to find the radius. So remember, right now we have the height, we have this piece, and we need this piece. So it's Jupiter. So if you go to your chart and look, you can find the radius of Jupiter is 7.818 times 10 to the 7th. And you want the radius of Jupiter, not Jupiter's orbit, because this object is above the surface of Jupiter. Okay, so the radius of Jupiter is 7.18 times 10 to the 7th meters. And then the height is 2 times 10 to the 7th meters. And so if you add these together, you should get 9 point. So the radius of the satellite's orbit, 9.18 times 10 to the 7th meters. So the first question wants the orbital speed. And you have AC and you have R. So you could use AC equals V squared over R. So V squared equals AC times R. So V squared equals 15 meters per second squared times the 9.18 times 10 to the 7th meters. Remember, that's going to be V squared, so you need to take the square root. And when you do, you should get 37,108. 108 meters per second. That's the orbital speed. And then it wants to know what's the weight in orbit, Fg. And we know Fg is just equal to mg. And it told us the m was 800 kilograms. And it told us the g was 15 meters per second squared. So Fg is equal to 1,200 newtons. Okay. Number 5. Number 5's the fun one. Okay, so number 5 says, a satellite which weighs 20,000 newtons on Earth. So again, you can find the mass, because it's just going to be Fg over g, or 20,000 newtons over 9.81 meters per second squared. So it should be 2,038 point something. 74. I can only do so much in my head. Okay, is put into circular orbit around Saturn with an altitude of 700 kilometers. So it's telling us the H is 700 kilometers, or 700,000 meters. And it says it's above Saturn. So the R of Saturn on our chart is 6.03 to the 7th. 6.03 times 10 to the 7th meters. And that's 1, 2, 3, 4, 5. So the radius of orbit, when you put these two together, of the satellite should be 6.1 times 10 to the 7th meters. All right. So then it says, calculate all these things. And then it says you cannot use the mass of Saturn in A to D because you need to solve for it in E. So A wants to know the time for one orbit. So we're looking for period of the satellite. So if you look at your sheet, for the things that have period, we have this one that has the period of the satellite, the R of the satellite, but we need another R and T. We can't use this one because we don't know the speed, and we can't use this one because we don't know the mass of the central body. So it has to be the R cubed over T squared equals R cubed over T squared. And the thing is, to use this one, so it's going to be R of the satellite cubed over T of the satellite squared. And we need something else that's orbiting the same central body. So this is where we go to the lower chart, and we have a whole bunch of moons of Saturn. Now, the answers that you have are for the first moon. I always pick the top one. So it's going to be Mimas. Okay, so this will be R cubed of Mimas over T squared of Mimas. Now, we need to do a little bit of work to get the R cubed and T squared of the R of Mimas. So if you look at the chart, it tells us it's 1.95 times 10 to the 5th kilometers. In other words, it's 1.95 times 10 to the 8th meters. Now the T for Mimas is given to us, if you look, as 0 days, 22 hours, and 37 minutes. So 22 hours, 37 minutes. So take your calculator and multiply the 22 hours by 60 to get the number of minutes, and then add the 37 minutes to it, and then multiply that by 60 to change it into seconds. Okay? And when you do all that, I'm looking for where I did it, you should get 81. So this should be equal to 81420 seconds, which is what we will use then over here. Okay, so we go back to our equation, and we're looking for T of the satellite. So cross multiply, and you'll end up with T of the satellite squared equals R of the satellite cubed times T of Mimas squared over R of Mimas cubed. Okay, so now fill your numbers in. T of the satellite squared will equal R of the satellite 6.1 to the 7th cubed. T of Mimas we just found. It was, what did I just say it was? Good question. 81420. 81420 seconds squared, and then R of Mimas was the 1.95 to the 8th. 0.95 to the 8th, and that's cubed. Okay, don't forget to take the square root after you punch all this in, and when you do, you get 14,245.38 seconds. So that's part A of number 5. Part B says the orbital velocity. Well, now that you have T, you can do V equals 2 pi R over T. So V equals 2 pi. The R was 6.1 to the 7th. And the T was 14,245.38 seconds. And you get a speed of 26,905.17 meters per second. Part B, I'm going to run out of time. Shoot. Part C wants to know weight in orbit. So you can't do FG because FG equals GMM over R squared. But you know Fg is equal to Fc, so you can do mv squared over r. So the mass was 2,038.74 kilograms. You just found 26,905.17 meters per second squared. And the r for Mimas was, or for the satellite was 6.1 times 10 to the 7th meters. And when you do that, you get an Fg, which is an Fc, to be 24,000